I must say that I have to apologize to the public and to Khadim because I was prepared to introduce Lucas Ambrosio. The program changed. I have not been told, and so my introduction will really
No
be
problem.
brief. I'm sorry.
No problem.
So it's a pleasure to introduce one of our youngest colleague, Khadim War, and he will speak about the proof of Verjovsky conjecture. Thank you,
Okay.
Khadim.
Thank you, Claudio, for the introduction. And I'm very honored to be a speaker in this 70th anniversary. And I'm also very happy to speak about these very recent results that I've been working on in the last maybe 6, 7 years, which is like a continuation of my PhD thesis. And yeah, so I'll be using both slices and Blackboard. Uh, in this talk, I will be considering I have a smooth manifold, closed Riemannian manifolds. Okay, the examples you can think of are the torus, manifolds of negative sectional curvatures. So we have this definition of Anosov diffeomorphism. So you have a diffeomorphism on this manifold is said to be Anosov if you have this splitting, which is invariant, and also you have a hyperbolicity condition, like the stable ES, which is called a stable bundle, is known to be contracting in the future, and the unstable bundle is contracting in the past. There is this alternative definition of Anosov diffeomorphism, which is via Fields, which is actually very interesting, as I will say later why. So a diffeomorphism is said to be Anosov when you have this family of cones. At every point you have two cones, stable and unstable, where the unstable cone is forward invariant, and the stable cone is backward invariant, and you have certain hyperbolicity when you are inside these cones. This definition is interesting because it is open. Okay, so see what we have here in this condition is these are open. Like when you have a diffeomorphism that is close to F, it will still satisfy these properties because the differential will be closed. So you fix the same cone. So it kind of tells you that the being Anosov is like an open condition. Okay. Yeah, so that's what I said now. And part of the results I will talk about belongs to the bigger problem of finding abstraction of manifolds to have this type of system, like hyperbolic systems, uniform Anosov systems. So already in dimension 2, you can see that the only orientable surface that has Anosov diffeomorphism is a torus. Just because when you have an Anosov diffeomorphism, you have these bundles, up to orientability, you can suppose that you have non-vanishing vector fields. And this you can only have it on the torus. And also in higher dimension, you can see that like spheres, for instance, like 3 sphere cannot have such a system for same topological reasons. Okay? So an example of Anosov diffeomorphism is given by these automorphism of the tori that doesn't have eigenvalue 1, okay, of modulus 1. And there is this nice theorem by Newhouse that gives a classification of codimension 1 Anosov diffeomorphism in general. So codimension 1, it just means that the dimension of stable or unstable is 1. So this theorem by Newhouse said that if you have a diffeomorphism that is Anosov in codimension 1, then it has to be like a total automorphism, okay? One of these examples above. So, yeah. So from along the same line, we also define here, I have a point I forgot, sorry. Yes, similar definition, you have also an Anosov flow, which beside the two hyperbolic bundles, you have a fluid direction. Okay, this is just a neutral direction. And you have also that these bundles behave like, they are hyperbolic. They are invariants, and you have contraction by the flow. And if the dimension of ES is 1 or dimension of EU is 1, we say that F is of codimension 1. Okay, examples of Anosov flow. One example is a suspension of an Anosov diffeomorphism. Like you have an Anosov diffeomorphism on a manifold, let's say just a linear total automorphism, and you can pick a function R, which is called a root function, and from there you can define this suspension manifold, using this equivalence relationship. And this flow will be an Anosov flow. There's also another class of examples of these flows, which is like the geodesic flow in negative curvature. So the geodesic flow is a flow that is happening on the unit tangent bundle of a Riemannian manifolds. And yeah, so you pick a direction on your surface or on your manifold in general. You draw the geodesic up to time t, the unit speed geodesic, and the velocity at time t is the image of the starting point by the geodesic flow. So that's the definition. So if you have negative sectional curvatures, this is an example of Anosov flow. These two flows that I talked about, they are very illustrative to what I'm going to say, because later on I'm going to say flows that have section and flows that do not have section. So these geodesic flow, they are examples of flow that do not have a global smooth section. And the suspension flow, they have sections. So Verjovsky conjectured this, that every codimension 1 Anosov flow on a manifold of dimension greater than 3 is orbit equivalent to a suspension of a total automorphism. Okay? In some sense, this is, this being true, say that you have a section. So the flow that I'm considering here is not like the geodesic flow. Because the geodesic flow, for it to be codimension 1, it just have to be dimension 3, right? Like on a surface. And here we are dimension greater than 3. Later on, I will give a sketch of why we need these dimension assumptions for this. Okay, so there is a notion of integrability, which is different from the notion of integrability that Ugo was talking about. So this is integrability of bundles, okay? We say that the Anosov flow has joint integrability if there exists a foliation that is tangent to ES and EU, okay? So an example for this is, before, when I consider the suspension flow, you can think of a map on the torus, okay? And you take a constant time suspension, let's say time 1 suspension. So you have this identification, okay? These two are identified, okay, by the flow. You can see that ES, so in the previous example, when you take R is identically 1, you get that ES plus EU is integrable, and that the integral manifold, the leaves of the foliation is just given by these torus, okay? And the leaves. I should say leaves of the foliation of the corresponding foliation are T2. Are copies of T2. And so for the geodesic flow, this is not possible. It's not possible to have integrability of this bundle, because we know that the geodesic flow is contact flow, so this is not integrable. So there is this result by H and G's that prove the Verjovsky conjecture under some assumptions, okay? I mean, yeah, I should say why it prove it. It just gives an integrability result. So if you have a codimension 1 Anosov flow on a manifold of dimension greater than 3, if this joint is C1, like the joint of these two bundles is C1, then F has joint integrability. So at this point, I would like to write a sketch of this proof where you can see the use of these dimensions and codimension 1, okay? So suppose that you have an Anosov flow, so you have Ft that is from M to M. So you have a splitting of your tangent bundle. This is the flow direction, okay? And you have hyperbolicity, okay? So suppose that we have codimension 1, so we can say that dimension of ES is 1. So this is codimension 1. And yeah, dimension of the manifold greater than 3, it tells you that this is at least 2-dimensional. So the dimension is bigger than 2, okay? So let me just try to sketch a proof of this using a condition that the flow preserves a smooth volume. Okay, it's not like a big assumption. So suppose that Ft preserves a smooth volume. Okay. Now, this theorem by Shinji says that ES plus EU C1 implies integrability of ES plus EU. Okay. So the problem of integrability of these bundles is a problem that is solved by the Frobenius theorem, as we all know. So if the bundle is C1, this is integrable if and only if it is involutive. So here you can define a one form. There is a dynamically defined one form. So let eta be a one form so that eta vanishes on this. The kernel of eta is just ES plus EU, and eta is 1 on the flow direction. This one form is, if you are more familiar with geodesic flow, this is just the one form that defines the contact structure when you have the geodesic flow, okay? And this, by invariance of these bundles, you have that this is invariant by the flow. This one form is left invariant by the flow. So to prove integrability here, you need to prove that d eta vanishes on the kernel, okay? So integrability by Frobenius is equivalent to d eta wedge kernel of eta is 0, okay? Now see that, so d eta, if you put two vectors on the unstable direction, it is 0, okay? So d eta, if you take VU1, VU2, this is 0. Why? Because eta is invariant. So this is df minus t star eta of V1u, V2u. And this is d eta of f minus t star VU1, f minus t star VU2. And this goes to 0 because these vectors, they are contracting by the definition of these bundles. Okay? So to prove that this is 0, it's just enough to prove that when you put vectors, one is stable and one is unstable, this is 0. And by the way, this is something you cannot get. So if you are in the geodesic flow case, because this is contact, so this is just the volume form. Okay? Now what happened here is that this is the step where you need this this discrepancy on this dimension. This is one-dimensional. Let's say this is two-dimensional, just to simplify. If this is two-dimensional, it means that, and volume preserving, sorry. It means that the contraction here, the contraction you have here, beats any expansion on this bundle. Okay? So this is basically what I'm saying. Volume preserving and dimension of M bigger than 3 implies that, if you look at dft restricted to ES times dft restricted to EU, this guy goes to 0 as t goes to infinity. So for some people who are more familiar with dynamical system, this is a type of a bunching condition. So this is a bunching condition. So the discrepancy on the dimensions gives a bunching condition, and this.
That works as long as the 2 dimensions are different?
No. Because if the two dimensions is different, you don't know. You might have another vector here, which is beaten by guys here. Yeah. So codimension 1 is crucial here. So you will have dft star eta vs vu, which is d eta of ft star vs ft star vu. This guy, by this bunching condition, it goes to 0. So so when you have regularity of these bundles, the proof of integrability of ES and EU is easy, okay? And actually, Etchingis, in his paper, he wrote a nice word for IMPA that when he wrote this result, he was here at IMPA, this theorem in '87. So I should. So in the next lines, I want to show how integrability implies some topological abstractions. So, So there is this result by Plant in '72 that tells you that if you have joint integrability, that F should be a calligraphic F. With corresponding foliation F, then we have that the leaves are compact, and you have when you restrict, when you take the return time map to one leaf, that is an Anosov diffeomorphism. Not only is an Anosov diffeomorphism, it is conjugate to a total automorphism. The fact that it is conjugate to a total automorphism follows from a result by Franks and also Newhouse. Okay, so integrability here, you can see that it gives this nice way to write your manifold as a suspension. And there is also this other result that tells you why integrability is not the general condition you would hope to get. So if you have a this F is a floor. This should be calligraphic F. I'm sorry, this guy here. That's a typo. This is a calligraphic F. Okay. If you have a codimension 1 Anosov floor, which is jointly integrable with corresponding foliation F, if you have this one form, the one form I just defined here, then the leaves of the foliations are compact. And not only that, any pair of periods of eta, so the periods of eta are given by this. So you can have a map from the fundamental group to R that is given by you integrate eta along this. So the image of this map are the periods, and the periods are rationally dependent. So what does it say? This says in particular that if you have integrability, any two periodic orbits are rationally dependent. And that is kind of very strong condition in general to have, easy to destroy. Okay? So from this, you can just say that if you give me an Anosov floor, I can find a perturbation to destroy integrability. Thus, in the same line, we have this theorem by Breen that non-integrability is open and dense in the space of Anosov flows. Okay? So now we prove this conjecture here, and yeah, so the rest of the talk I would be probably spending it on the blackboard to tell you how we do this proof. First of all, we have this condition of special synchronization. What does it say? It says that you have a one form that contains the stable bundle and the Lie derivative of the stable with respect to alpha is 0. Okay, this sounds very artificial, but let's see that special synchronization implies integrability. Opa. That's not what I want to say. Yeah, special synchronization implies joint integrability. So let me spend. The ideas is just along these lines. So so you have alpha is a one form. Says that the stable is generated by a vector field x. Okay, is one dimensional. Is in the kernel of alpha. You have alpha of z is identically 1. From these properties, if you want, you have this lemma just from the domination that if you take f t star, f minus t star of alpha is converging to eta, where eta is a limit one form you get that defines the limit bundles. Okay? So whenever you have such a one form, you have that f minus t star alpha goes to eta. It's not difficult to prove because x is in kernel of alpha. That means that x is also in the kernel of this guy because x is invariant by the flow. X is in the kernel of f minus t star alpha. So this t goes to infinity. Okay? This is by invariance. This is because f minus t star x is some function lambda t times x. And you see that this one form also, it satisfies the property that f minus t star alpha z is identically 1 all the time. But if you take two vectors in the unstable bundle, you said f minus t star alpha of VU. This is just alpha of f minus t star VU, and this goes to 0, okay, as t goes to infinity. So this tells you that you have this convergence. And so to find integral manifolds, to integrate this bundle, it makes sense to try to integrate this family, okay? And so there's a problem here that one faces is you don't have regularity of this limit bundle either. So you cannot say, like this guy either, in general, it's just holder, okay? Unlike the assumption that in the theorem of exchanges, this guy is just, in general, holder. But there's a theorem, there's a formulation of integrability by Hartmann, which I also generalized in my thesis, which is, a continuous one form can have exterior derivative. Even though it is just Hölder continuous, it can have exterior derivative. Okay, just look at this example. I mean, it's not a good example, but let's suppose that if you have phi is a C1 function, you can take eta as d phi. This one form has an exterior derivative, and it is 0. So the definition of exterior derivative by Hartmann is just so eta has exterior derivative if if there exists a two-form beta such that you have the Stokes formula holds. So J, where J is a Jordan curve and D is a disk that bounds J. So this is a way to define exterior derivative. And also Hartmann has a I mean, it's something that, you know, intuitively you can hope that if you can approximate this guy by smooth one forms where you have control on the exterior derivative of this sequence, you would have it at the limit. So what happened here is that if you have so there is this proposition that spatial synchronization implies that eta has an exterior derivative. Eta has an exterior derivative that is 0. Has an exterior derivative that is 0. Why is so? Let's try to estimate the exterior derivative of this guy. So if you want, if you write df minus t alpha, if you put two vectors EU, this is 0 by, you know, by the fact that you have contraction on stable in backward time. So if you put now df minus t star alpha at x and VU, this guy is also 0. Why? Because, I mean, simple algebra tells you that this is just the lead derivative x of f minus t star alpha applied to VU. And the spatial synchronization is just a condition that Lx alpha is 0. So if an Anosov flow is spatially synchronized, you have integrability. You have joint integrability. Okay. Now, I should see how much time I have. Okay, I have time. Okay. Yes. So you see that this sketch how to prove using this Hartmann notion of exterior derivative, this proves that if a flow is spatially synchronized, it is jointly integrable. Now the main problem is to find, so the main problem, find a reparameterization. So given F, that is an Anosov flow, the main problem is to find a reparameterization such that this reparameterization is spatially synchronized. So find a reparameterization. Since I'm only interested in orbit equivalence, so orbit reparameterization doesn't leave the orbit equivalence class. Find a reparameterization that is spatially synchronized. Spatially synchronized. Find a reparameterization that is spatially synchronized. This turns out to be a very delicate and difficult problem, because so how do I formulate this problem? How do I formulate this problem? So I'm looking for a function. So find a function C from M to M, M to, let's say, 0 infinity, it is positive function. Let's say it is C2, such that you have this, if you define this vector field, Z phi equals Z over phi, and you have the corresponding flow, which is F phi, generated by Z phi, you want to find such a phi such that an alpha such that this Lx phi, alpha phi is 0. So alpha phi is also, a one form that contains that the kernel contains x phi, and it is 1 in this direction. Yeah, so the problem is to find this function, actually. And so by easy algebra, you can see that, it is easy to see that Lx phi, alpha phi at x phi is 0, and Lx phi, alpha phi, whenever alpha phi is a one form that satisfies those conditions of Z C is 0. This is easy, okay? This is just because x phi is in the kernel of this guy. And this is because of the, how to say it, of the fact that this flow lives invariant x phi. So you can have that x phi, this Lie bracket will be in the direction of x phi. So a question you might have is, I've been saying that these bundles are Holder continuous, but I'm taking Lie bracket of x phi. But what happens is, if I am on the space of volume preserving, if I do a reparameterization with a smooth function using the same discrepancy, the same bunching condition, I still have x phi is C1, okay? So bunching condition. Bunching, which is the same as uses the discrepancy. So this is using codimension 1 and dimension of M bigger than 3. Bigger than 3, yes. Yeah. This implies that x phi is always C1. Actually, this is a result. It was a remark I found in the paper of Plant when I was reading this paper in 2016. And when I first talked to people about this remark, that codimension 1 and dimension greater than 3, volume preserving implied this, it was surprising to many people. And that's how actually we got to write a paper with another co-author about mixing for these type of examples. But this is very important here. The discrepancy on the dimensions is something very interesting. And volume preserving, okay? Because you need volume preserving to say that the stable beats any expansion. So if you have these conditions, you have this bundle is C1, so this equation is, it makes sense to write this.
Could you remind us what is the definition of x?
Yes, that's a good point, actually. That's what I was coming to next, which is this Parry, which gives an explicit formulation of xc. So xc is of this form. That's what makes this difficult, actually. Okay, this sounds very involved. So this is from Parry. He was the first one who found this formulation.
What is x?
X is the original stable bundle. The stable of the first flow you consider, okay? So, yeah. Because it is stable, the definition gives, uses all the feature of the point. So this is actually what makes this equation difficult to solve. And if one writes the equation, this is what you get.
X itself is not C1.
So we start with X that is C1. We start with a volume preserving codimension 1, higher dimension, bunching condition gives X is C1. Any also reparameterization will have C1 stable. So if you do some algebra on this equation, this is what you get. And a priori, there is no, if not the dynamics, I would say there's no hope to solve this equation. Oh, G phi here, G phi is this quantity. And there are some other quantities. U is the unstable Jacobian. U is d over dt of log of the Jacobian of dft restricted to ES. Okay. It's very involved when you write this equation. Now, and this is an equation that even to hope to get, this equation satisfied at a point is tricky. It's very difficult to hope to get this equation satisfied at a point because when you pick a point, there is this term that depends on the orbit. And this orbit might be accumulating to the points that you consider. So this is a very difficult equation. So the way I solve this equation is I found a method to solve it at a periodic orbit. If I consider a periodic orbit, I can make a perturbation of a function that is 1 to make it this. So we solve the equation. So there's an algorithm to solve this equation along periodic orbit for given periodic orbit. P. I mean, also you need to say that you need to have, a uniform size disk that the orbit is not coming back. That is also crucial here, that, you cannot have this orbit accumulating itself, otherwise you will not control the second derivative of this function. You have that problem, okay? So how do we solve those, So we want to solve this equation globally on the manifolds. But our way to solve this equation, we know how to solve it along a periodic orbit. So here we use the fact that periodic orbits are dense. Okay, if you fix the periodic orbits are dense here. So periodic orbits are dense. So if you fix a periodic orbit of length t, you might have this problem that I'm saying that this orbit might be, accumulating to itself before it closes out. The way to solve this problem is you go to a finite cover. You go to a finite cover of your manifold, and the cover depends on the fundamental group of this closed orbit to guarantee that you can have space around this orbit, that the orbit is not accumulating. So, if you have your base space that is this, and you have a periodic orbit that might be accumulating, doing crazy things, you can go to a finite cover. And this periodic orbit will give rise to finitely many closed orbits. And in each of these, you fix one lift of this, and you can apply the algorithm I said here. There's an algorithm here that solves the problem along periodic orbit. You can solve it here by, taking a nice neighborhood, tubular neighborhood of this periodic orbit. And you use the group transformation to say that this function applies to the group. So if you have here phi tilde, you can have the same, the function which is, there's gamma that maps, there's elements of the fundamental group that maps this guy to that. You would have that phi here will be just, you can apply this to phi tilde of this gamma. Okay? In that way, you would solve the problem along these periodic orbits. And you can use by definition that this is equivalent by the group, by the extension, by the covering you consider. And you can project down to this, to the surface, sorry, not the surface, to the manifold you had originally. And in that case, you would have solved this equation on a longer piece of orbit. And this piece of orbit, you can take them to be delta dense or epsilon dense, and you take epsilon going to 0. And if you do that, you know, this procedure tells you that you can control, gives a control on the second derivative of the function you are looking for. So you can have a sequence of function that is converging to this guy here that satisfies this equation, basically. Yeah. So, yeah. So.
You need a uniform estimate from the orbits.
Sorry?
If I understood correctly, you find alpha
Yes.
on each periodic orbit.
Yes.
Then
you go to the limit, yes. There's a uniform estimate, yes. There's a uniform estimate on, yes. There's a uniform estimate along this sequence of orbit you choose, yes. Okay, because just trying to solve this equation on the manifold, you cannot do it, because if you take a periodic orbit that is accumulating, at least I cannot do it. I cannot find.
So what is the regularity that you get?
Actually, it will be C2 plus theta. Sorry, I said that these x are C1, but they are actually C1 plus. And this equation, if you look at the right side here, is theta, is Halde. And this side is the second derivative. Basically, the way I solve this equation is via, a type of discretization. I found at step n, I use the function at n minus 1, I plug it here, and I define the function at n, and I do that recursively here. So the function I get will be C2 plus theta, and it satisfies this property, and it gives integrability. And once you have integrability, you use plans and so on to find a section and to say that this flow is conjugate to a suspension of a total automorphism. There's one point here that I forgot to mention, is I have the volume preserving assumption. But this is really not an assumption, because there's a result by Azaoka that tells you that every codimension 1 Anosov flow is topologically equivalent to a smooth codimension 1 that preserves a volume. Is orbit equivalent to a volume preserving one. So yeah, so this is roughly the ideas of the proof. And if you see in this equation, already the bunching condition is used, because when you talk about the derivative of this function here, you need the stable to beat any other vector when you take the derivative of this function here. And yeah, the bunching is the discrepancy on the dimension and the volume preservation, okay? So yeah, so this is what I wanted to say, so, and fine. Mm-hmm.
So, are there questions?
Well, this is just a condition that I found, when I was in my PhD thesis. Whenever I wanted to integrate these bundles, I tried to approximate it with just also along Hartmann's line. Whenever you want to integrate a continuous bundle, it makes sense to approximate it with with smooth bundle, and you control the regularity of the Lie brackets of this approximation. And if this Lie bracket goes to 0, you get that the limit will be integrable. Yeah, so to have, because the limit bundle, I cannot talk about Lx of the limit form because it's just not regular. So it makes sense to start with one guy that is regular, and that you can pull back to converge to the limit. Yeah.
Any other question? Well, if there are no further questions, let's thank Khadim again. Thank you.